Good morning. My name is Kawage Salim and I'm part of Group 9. I shall be taking you through the our project, which is generally about detecting counterfeitism in all currencies. Yeah, we are dealing mostly in the Indian currency, so I'll be taking you through that. Me and my colleague, but I'll be the first one to speak, and then you come again to give the visualizations of the idea. Um, I'll begin by defining our title. Of course, we're talking about the generative attention-based mechanisms of knowledge distillation for fake currency detection. Defining the key terms. If I'm to define the key terms, the word knowledge distillation is whereby you get a student model and a teacher model. The teacher model, we take it to be having a lot of inaccuracy, and then what we do have to train another student model, of course, which has a lot of accuracy and uses less data compared to the teacher model. And going to the abstract, of course, we know counterfeit currency threatens the financial security. For example, if I use a case scenario of Uganda, in December last year, the Post Bank of Uganda gave almost 500 million Uganda shillings to a customer, and this is something that was threatening the financial economy of Uganda. So from there, we are having a proposed solution. Of course, in the proposed solution, we are having a system that will be AI-driven, combining VITs, which are vision transformers, GATs, which are graphical attention networks. We are having GANs, which are which are I've just forgotten. But then we're also having knowledge distillation and feature extraction as part of our algorithms that we shall be using in this scenario. Then I'm introducing the background of what you're talking about, counterfeit currency. Like I had said in the previous slide, it's a problem that is being so critical to the financial sector, whereby it's hindering a lot of economical it's hindering out of a lot of economical issues, whereby, for example, it brings about inflation in the economy. So we know that traditional methods, for example, whereby we use the feel and touch method, whereby you see you have to first put the note on the light to see the watermarks. Those are all traditional methods, and we've seen those are hard to identify the forgeries, because these guys who are forging the currency right now use robustic means. So I think the next slide will be defined as vision transformers. Vision transformers, of course, they get pictures and divide them into patches, like here how we are seeing, and then graph attention networks. There are model structure relationships between security features. That's why they show. Then you are having generative adversarial networks. This one generates synthetic counterfeit samples for model improvement. For example, when you're having limited data samples. Then I'm talking about vision transformers. Here, specifically, vision transformers use a set of patches instead of the entire images. They extract patches from the data samples, and then the patch is analyzed individually to get the final thing. And then generative adversarial networks, these ones work on a two model interface, whereby you have the generator and the discriminator. These ones work specifically when you're having a limited data set and you want to create synthetic samples. They also have the graph attention networks. These ones assign the target nodes, the target feature as nodes. We are also having the knowledge distillation, like I said, whereby you get the student model and the teacher model. The teacher model is taken to be inaccurate, and the student model is taken to be more accurate than the student model than the teacher model. So that's why I use knowledge distillation. And also the current research trends, we're having the CM, convolutional neural networks. These ones are are used, but of course they struggle with long range dependencies. We're also having multimodal learning, whereby they combine, it's some kind of hybrid. They combine the images, textures, and sound, and this one enhances detection. Also having transfer learning, which improves model accuracy with fewer training samples. These are the features of the currency that we shall be working with. And then the methodology, what we do, we have the data pre-processing. Of course, this one has resizing, normalization, and augmentation. Augmentation generally, it's about generating variations. For example, in the node flips, and then we also have feature extraction. Feature extraction is whereby we have to use VITs to generate the features on the currencies that we are having. Then next we are having the real or fake prediction. In this sense, the objective here is classify banknotes as real or fake. Then which algorithms shall we be using? Like I said, we shall be using visual transformers, graph attention networks, tradition features, extraction using SIFT and ORB. Then here we are having GANs for synthetic fake currency images in case the data set is not enough. Then also have enhanced training data. We have to train the data to enhance it. The hybrid, which combines VITs, GATs for classification models, knowledge distillation to convolution neural networks. And of course, all these three are inaccurate, and they won't finish what we want. So that's why we bring in the lightweight CNN model to combine all the features like that said. And then what is left is about deployment, the real-time inference, whereby we deploy our system to mobile apps and other software platforms. My colleague Adi from
Thank you very much. My name is Kasha Alvin Sadi. I'll be taking you through the EDA analysis on the visualizations we managed to come up with in the data. Where we carried out the EDA is just simply because we wanted to understand this very data set we had acquired, and then also clean some of the data, find out missing values, and then also deal with the outliers. Then after that, finally, we came up with these visualizations. So the one you can see on your left here, it's a class distribution. This just simply displays like the number of images you can see on the y-axis and also the different categories in terms of the data set. So this simply means that for the first bar, you can see it means that there are just 15 images in the fake training folder and so on and so forth. Then for on the right-hand side, we have a stacked bar chart. This one just simply brings out a clear breakdown of how images are arranged actually in categories, or you could think of them as subsets. So for the training, the fake, these carrying, you see this purple one represents the fake, and then the yellow represents the real currencies. So they're just stacked in terms of splits, and then a clear breakdown is achieved. Then next, we talked about earlier on brightness and then noise, the images that we had acquired from our data set. And then we wanted to understand how the brightness was distributed, and this was achieved by coming up with a histogram showing the distribution of brightness values or levels depending on the number of images. So on your y-axis, we have the frequency or number of images, then the brightness level, and then a smooth curve to show how actually the brightness varies very well to check for the inconsistencies in the lighting conditions. Then if brightness varies a lot, it means that we need to have normalization techniques to come up with better estimates, and then enhance model performance. Then for image noise, the noise that was captured in the images, we came up with a histogram as well. And then frequency, those are just number of images. Then the noise level, we express it as standard deviation. So this simply means that higher noise levels, you could see this, and higher noise levels around here, yes. Gross images would indicate possible distortions in fake notes or poorly scanned images. So if the noise is significantly different between real and fake notes, then it could be used as a distinguishing factor. Then we came up with a CDF for image brightness, and you could think of it as a geometric probability distribution, just to come up with a way of determining the percentage of images falling within a specific brightness level. So the geometric distribution is on your axis, then the brightness level is on the x-axis, and it can help to determine the processing stage of this. You can also think of it as the growth histogram equalization that would be required, and then also determine how actually the probability of the next image is in line depending on brightness. And then on your right, we have the scatter plot that had two axes, and we're having comparing brightness with feature against noise in the images. So the relationship, we're just establishing relationship between brightness and noise using scatter plots. And then if of course fake notes don't have higher noise or lower brightness, this could be used as a feature as well for clarification for classification. Then next also wanted to know the amount of outliers in the brightness, and we came up with a box plot for that to just detect outliers. We could think of them extremely bright images and just understand the median and range of brightness. So the box here is the median that contains then all the brightest levels that lie within the whiskers are considered valid, then those that outside the whiskers are known as outliers. Then also a correlation heat map for the brightness and noise, just to ascertain if there is a correlation that exists. So if a strong correlation, you could see of this and this actually exists, to simply mean that also against that lighting conditions impact noise levels, and this will help decide whether brightness normalization should be applied. Then also had a two density plot brightness against noise, and we used the KDE plot, and we came up with a density. The blue density you can see it simply means that these two, the noise level and brightness, are actually of high density, and where we needed this just simply to ascertain whether we would need these very features to understand how they relate, and this would help us identify clusters for real and fake notes, or they might differ also for feature engineering. The models will be using. Then the pixel intensity histogram on your right was just to ensure the distribution of pixels values across the image dataset ranges from 0, then the maximum is 255, the frequency and the number of images in the dataset. Then what it suggests means that highlights variations in the brightness and contrast within the images necessarily means that it helps analyzing texture and shading differences between actual, real, and fake notes. Think about the colored images and also those that are in grayscale. Then the problem statement finally. Application problem, this was actually counterfeiting, bypassing traditional verification methods such as UV lighting and so on. So we wanted to come up with an automated and scalable detection method to deal with this. So the technical problem was actually that banknotes have dimensional image data, and then there was also need for deep learning models to prevent this actual overfitting that goes in the segmentation. Thank you very much. I remain Kasha Alvin Sali.